Hello and welcome to the Daily Space. I'm your host, Dr. Pamela Gay,
And I am your host, Beth Johnson.
and we are here to put science in your brain. Sometimes science is just pretty. Researcher Christopher Dupree and his students have acquired new high resolution images of the W49A star forming region using the Very Large Array. Combined with data from the IRAM Northern Extended Millimeter Array, they were able to spy new details. According to the paper published in the Astronomical Journal, these observations reveal new morphologies, new structures to the forming stars and their surroundings. This includes a bipolar structure associated with one of the stars, and the revelation that one of the sources can be resolved into three different glowing points in the higher resolution images. What all this means, that is for another paper and another day. For now, we encourage you to go to our website, dailyspace.org, and check out this image in full high-resolution glory.
One of the awesome things about studying space and astronomy is the science can jump between being really darn pretty and really darn meaningful. Astronomy can answer, how did it start and how will it end? And with planetary science, we can look for, where might there be life? Before we found planets, it was good enough to say if a planet is in its star's habitable zone where water can be liquid, it could have life. But now that we are finding planets in that place, we'd like to be a bit more specific. Researcher Brendan Dyke and his team have taken inspiration from our own Earth as they look for the answer. And it turns out it all comes down to the iron. According to Dyke, just because a rocky planet can have liquid water doesn't mean it does. Take a look right in our own solar system. Mars is also within the habitable zone, and although it once supported liquid water, it has long since dried up. Our findings show that if we know the amount of iron present in a planet's mantle, we can predict how thick its crust will be, and in turn, whether liquid water and an atmosphere may be present. It's a more precise way of identifying potential new Earth-like worlds than relying on their position in the habitable zone alone. Measuring the amount of iron in the mantle of a distant planet isn't something we can do today, but it may be possible in the future. JWST should open the door to exploring the chemistry of alien worlds, and here is to hoping that much delayed telescope someday flies and functions.
One thing that always gets me about astronomy is that with proper technology, it is easier to observe planets orbiting other stars than to understand the effects of dust and magnetic fields on how we see and what we see beyond our galaxy. To be fair, it could just be that we already have the right telescopes to see alien planets, but we're only beginning to develop the tools to effectively study things like magnetic fields. This possibility is hinted at by new work led by James Chibuzi that uses the Meerkat radio telescope to look at a bright galaxy named MRC 0600-399. This galaxy is 600 million light years away in the merging galaxy cluster Abell 3376. This system has an active black hole in its core, and as material streams toward the black hole, it generates powerful magnetic fields that shoot particles out in jets like railguns. Radio telescopes, like the relatively new Meerkat Observatory in South Africa, can see these jets. And new observations, they reveal the jet mashing into the boundary between this galaxy's subcluster and the greater galaxy cluster beyond. Simulations by co-author Huuji Sakimi reveal that what they are seeing is in good agreement with models of interacting magnetic fields at the boundary of the subcluster and cluster. This arching magnetic field bends the jets, creating dramatic scythe-shaped structures. Meerkat is a precursor system to the planned square-kilometer array. And with that future telescope, maybe understanding magnetic fields will get a bit easier.
As much as we may know about our universe, there is even more that we know that we don't know. Gamma ray bursts, the random flashes of some distant something we think are associated with supernovae, These fall into the category of things we know we don't fully understand, and every piece of data we can get is gladly welcome. As Pamela has experienced, if you're using a telescope that might be able to see the optical counterpoint to a gamma ray burst, you may get asked to stop what you're doing and move that telescope to look for that brief optical afterglow. For one telescope, however, no repointing was required. The TESS spacecraft just happened to be looking for planets in the part of the sky where a distant gamma ray burst was spotted by the Swift Bat satellite. That is an awesome name. Normally, this telescope can look for afterglows on its own, but with its super wide field of view and a photobombing moon, this time it couldn't. The lucky coincidence that TESS and its smaller field of view were looking in just the right place meant that data was collected. The optical afterglow was at its brightest 1,000 to 2,600 seconds after the gamma rays were spotted, and within 7,000 seconds, that glow had faded beyond Tess's ability to see. We don't yet know what new science may have been learned, but this is such a cool coincidence we had to share. After the break, we'll be back to talk about more things that go flare and flash in the night.
Telescopes like Swift and TESS do their jobs by systematically surveying the sky over and over and over, looking for things that change. Their repeating series of images means we can easily see when something flickers or flares in the night, and we can go back and see what was there prior to the flash. TESS and Swift are just two of myriad survey scopes out there looking through large sections of the sky each night or each orbit as astronomers look for supernovae, asteroids, and other rare events like microlensed starlight. Anytime you notice a lot of comets with similar names, like Neowise, Atlas, or Pan-STARRS, what you're hearing are the names of survey scopes that happen to find new comets at a regular cadence. The Pan-STARRS telescope on Haleakala in Hawaii is used by a number of different surveys, including the Young Supernova experiment that works to catch the first light of relatively nearby exploding stars. In 2019, it spotted one such explosion in spiral galaxy NGC 4666. This galaxy is a regular target for both professional and amateur astronomers. And it turned out that not only was there survey data on this object, but for unrelated reasons, the Hubble Space Telescope had observed the location of this supernovae, named 2019 YVR, just 2.5 years prior to its explosion. These images provided astronomers the rare chance to study exactly how a star looks prior to its explosion. In this case, the star they observed was a yellow star that should not have produced this kind of a supernovae, which is perplexing. Basically, supernova 2019 YVR was observed to be a perfectly normal hydrogen-free supernova. The Hubble images, taken, like I said, just 2.5 years before the star's explosion, they show a yellow star, which means the star had hydrogen in its outer layer. So where did the hydrogen go? This work appears in monthly notices of the Royal Astronomical Society and is led by Charles Kilpatrick, who explains, if a star explodes without hydrogen, it should be extremely blue, really, really hot. It's almost impossible for a star to be this cool without having hydrogen in its outer layer. We looked at every single stellar model that could explain a star like this, and every single model requires that the star had hydrogen, which, from its supernova, we know it did not. It stretches what's physically possible. So again, we ask, where did the hydrogen go? According to the press release, several months after the explosion, Kilpatrick and his team discovered that the material ejected in the star's final explosion seemed to collide with a large mass of hydrogen. This led the team to hypothesize that the progenitor star might have expelled the hydrogen within a few years before its death. Kilpatrick goes on to explain, astronomers have suspected that stars undergo violent eruptions or death throes in the years before we see supernovae. The stars This star's discovery provides some of the most direct evidence ever found that stars experience catastrophic eruptions, which cause them to lose mass before an explosion. One additional possible explanation also exists. It could be there is an invisible hydrogen thieving companion star involved, a star that stole the hydrogen in the couple of years before the supernova and after the Hubble image. Maybe. We don't know for sure. But as astronomers like Kilpatrick watch the supernova evolve, we may be able to figure it out in the next few years. When we know more, we'll bring it to you right here on the Daily Space. After the break, we'll be back, and Beth will discuss one of my favorite topics, volcanoes.
We are, as everyone should know by now, huge volcano stands. And the last month has been amazing for all the volcano watchers around the world. We have had our fill of lava pouring out of a cinder cone and fissures in Iceland, as well as some scarier explosive eruptions at La Soufriere in the Caribbean. But we're not the only ones keeping an eye on volcanoes these days. And no, I'm not talking about all the webcams around the world. I'm talking about the Volcanic Cloud Analysis Toolkit, or VolCat. VolCat is a complex set of software that scientists use to process data from remote sensing satellites in near real time. And with that software, they can detect and track the volcanic ash clouds that rise up into the atmosphere. For the most part, this analysis lends itself to mitigating ash-related hazards for aircraft, since the ash particles will destroy engines, so planes need to be redirected around these ash clouds. The Volcat software was the brainchild of NOAA scientist Mike Pavlois, who has spent his career watching clouds, and he realized about 15 years ago that analysts could not integrate all of the data coming in. And now his project uses 5 low Earth orbit satellites and 4 geostationary satellites to track more than 1,500 volcanoes around the world. The satellites have amazing sensors that help identify the radiation signatures specific to ash, separate from regular water-rich clouds. But it's not always that easy to differentiate the two types of cloud. As Pavlois explains, they're a mixture of volcanic ice, ash, liquid water, and volcanic gases. When there is no clear distinction between ash cloud and water cloud, VolCat tracks the cooling speed of the clouds instead. A volcanic eruption, and this should not come as a surprise to anyone, is very hot. And the ash clouds are also hot, and they get injected by the eruption into the cold upper levels of the atmosphere. And those clouds then cool rapidly compared to, say, thunderstorm clouds. That's where the geostationary satellites come in, as they can stay focused on a single swath of our planet and track the changes over time, observing volcanoes in their surveillance region every 15 minutes or so. In fact, they can take these images even more often, and La Soufriere was being imaged every minute during the height of its recent eruption. Of course, VolCat is only one piece of the volcano observing puzzle. We still need human experts to filter through the alerts from the system and check for any false notifications. It turns out that it's hard for even an automated system to process more than a terabyte of data per day. VolCat, however, makes it much easier for scientists to focus on where the ash clouds might be, and this means those 1-minute images become alerts in less than 2 minutes. Pavlois sums up the advancement. We are in a golden era because it was only less than 10 years ago that we were happy to get an image every 15 minutes. We imaged Soufriere's St. Vincent's clouds when they were on their way up, and that type of capability is really important. It's amazing how quickly technology can improve. After the break, we'll be back with this week's What's Up.
For you morning people out there, right now the moon is rising as a narrow crescent just before the dawn. Every day until May 11, it will appear to rise a little closer to sunrise, and it will appear ever so much thinner. This means now is your chance to really enjoy looking at faint things like the band of the Milky Way as it stretches across the sky. For those of you celebrating Ramadan, this tiny sliver of moon means Ramadan is almost over. Next Tuesday at 3:01 p.m. Eastern Time, the moon will be located on the same plane as the sun and the earth, and we will be unable to see it in the sky. As it orbits, it will slowly begin to be illuminated on its other edge as seen from the earth. And once the illuminated edge is seen, Ramadan will end. This means observatories across the Muslim world will be watching closely for that hours-old moon to be visible. For people of all cultures, the race to see just how young a moon can be spotted to the west of the sun, well, it's an astronomical challenge worth accepting. To see it, you have to point your binoculars, your telescopes, your eyes during the day at the spot the moon should be located and make out the faint crescent against the bright blue sky. I personally have never seen a moon younger than about a day, but in 2002, Mohsen Mirsarad spotted an 11-hour, 40-minute-old moon on September 7th. He was using binoculars and he set a new record. Observing the moon is something we do for many reasons. It's there and it's pretty, and these are perfectly sound reasons, and they are the reasons why I like trying to, well, photograph the moon against the horizon. The moon is also scientifically interesting as it formed, we think, through the collision of the Earth and another object we call Theia. The thud created a dense Earth, and the splash created the lower density moon. To better understand exactly what happened, we really want to explore all the different kinds of minerals the moon has. And because asteroids have hit the moon many times, we know some of the minerals from its interior have been tossed onto its surface. Ideally, we want to get our hands on these free samples from deep in the moon, and we want the freshest samples we can get. This means sending rovers, or humans, to the Schrödinger Basin, the youngest basin on the moon. In preparation for future exploration, Ellen Visplinsky and a team of students pored over lunar images of the lunar South Pole Aitken crater and Schrödinger Basin to map the minerals we most want to sample and understand. According to Suplinsky, when the Schrödinger Basin was formed, some of these lithographies, the general physical characteristics of the rocks, may have been uplifted from very deep below the lunar surface. Many of these rock types are exposed at the surface in multi-kilometer-long exposures of rock outcrops in Schrödinger's peak ring, an inner ring of uplifted rocks that form the basin.
Along with mapping the minerals, the team also mapped out 3 potential paths for future rovers, or maybe even humans, to explore. Now, with these maps in hand, we just need to land more robotic or biologic explorers on the moon. This has been the Daily Space.
You can find more information on all our stories, including images, at dailyspace.org. As always, we're here thanks to the donations of people like you. If you like our content, please consider joining our Patreon community at patreon.com/CosmoQuestX.